Anyways, let us start our lesson about work. If you recall, when we started our lesson about energy, we said energy was the ability to do work. So let's write it down. The ability to do work. And I said we would define work in a different way, the physics way, right? Let me fix this H. So it looks more like an H. There you go. The ability to do work. That is energy. So what is work? Okay. Before we move on, this should be an indication that energy and work are related. We'll see how. We're going to use two definitions for our class. And the first one is, it says, work is the product of the component of the force in the direction of motion times the distance through which the force acts. That sounds, somewhat dense, complex, and there is a slightly not as complicated definition, which is work is the product of the net force applied on an object and the distance through which the object is moved. And before we define work, or before we see what this means, I'm going to highlight words that I think and I'm confident everyone knows what they mean. So product, we know it's going to be multiplication, right? Component, vector, right? Don't forget we had components of vector. Force, right? Direction. We talked about force last unit with Newton's laws. And then motion. And then time, so of course has to do with product. Distance, right? So there's going to be a multiplication, vectors, so a force is a vector. So maybe we're going to multiply force times distance, right? And then we have to specify direction, and that is exactly what work is. So this is we can summarize this definition with the equation for work, which is capital W equals force, it's an ugly F, let's try that again, force times distance times the cosine of theta, right? And then let's define these terms real quick. F is force, in newtons, d is distance, in meters. And then, of course, the cosine of theta, that's a trig function, and then theta, that specifies direction. And in class, one thing I asked is, if you recall when you would go to the park when you were little and then you would see the swings, to get more speed, normally what we do is, if this is us, right, we kind of go this way, right? We get our feet, legs up, and then we kind of tilt back or lean back a little bit. So what we're trying to do is we're changing the angle, right? So if we take the floor to be like the horizontal, right, the ground. So if we are just standing, right, we would make a 90-degree angle. And so let's see what the cosine, let's say if we were talking about in terms of work, right, even though it's not exactly what's happening, it illustrates the point on why the angle is important. So let's see what the cosine of 90, so let's say you're just standing right next to the swing, or you're just like that, right? Yeah, well, not just standing, but let's say you were standing on the swing. That'd be weird. I'm pretty sure some of you did it though. And then you had someone push you, and don't try that. That's not something you should do anyhow. Let's pretend you did. If we get the cosine of 90 degrees, right? Oh wait, not 91. Oh, I can see the 0. Wait. There you go. Cosine of 90. That is 0. Oh, there you go. That is 0. meaning we're not doing any work in the physics sense. However, when we do this, right, when we try to get parallel with the floor, let's say if we get the angle, and don't think of it like that, right? Think about the distance from your feet and the ground. Oh, before I continue, this is not a weird glove. I use it for my writing pad. You know how on my Promethean board I said don't make sure your hand doesn't touch the board. Well, this allows for me to touch the writing pad and not do anything weird. Look, I'm touching the writing pad. So this is not weird. I'm not that weird, but whatever. Just so you know. So this is the ground, right? And then this is you. So if you are leaning back and with your feet up, right? So you can consider the angle to be 0, right? The distance from your feet to the ground, let's say if you were laying down, would be 0 degrees, right? That's 0. There's no distance. So let's see what the cosine of 0 is. The cosine of 0 degrees, make sure, look, I have degree. Where's my degree? Here, DG, degree. That is 1. What that means, guys, is if the angle is 0, that is the direction of the force is aligned with the direction of motion, like it's actually, aligned with it, then we maximize the work. So I need you to remember you're supposed to be taking notes, which I'm sure you are. Work is maximized I think this is how you spell it. Work is maximized when theta equals 0 degrees. And the reason why is because when cosine of 0 degrees. Oh, let me make this. Well, I'm going to write it again and then, because I don't know how it looks. I'm going to explain. So when the cosine of, you get 0 degrees, the cosine of 0 is 1. What that means is the work would be simply the product between the force and distance. That's it. In this case, you consider the force to be your own weight, right? Mass times acceleration due to gravity, and times the distance which you're moving. And of course, you can think about your changing momentum, which we're going to talk about next unit. But for now, I think that example illustrates why the angle is very important for work. So then we said that work, oh, that's weird. Work is maximized if this is not how you spell it, please tell me. I'll correct it. That's okay. When theta equals 0 degrees. Okay. And then I'm sure when I was talking about the equation, you just saw that work equals Newton meter, right? Newton times meter. And I'm sure you know this is the joule, just like energy. So they're very related. They have the same units. So make sure you state that there. Units, or unit, right, for work. That's the joule. Then abbreviation is capital J. Okay, so that is one definition for work. You're going to use it in your homework and I think for the exam. And you could use it even for the lab, which we're going to do next week. Now, for now, however, I want to define work in a different way. This is the second definition. It says, work is the energy transferred across the system boundary. So when we had energy and we were doing the schema, right? We had a system boundary. We included everything in our schema, and that's the boundary. And the fact that we included everything allowed for conservation of energy to be very easy to do with the pie charts. Now we're going to do something very similar, right? But before I go about the example, I want to read this definition again and then give you an equation which I'm not going to name because it has a very specific name, but that's okay. I just need you to write it down and see what that means. It says, work is the energy transferred across the system boundary. So work is energy transferred, right? Energy transfer is work. In this case, we can say net work. Don't forget that net is the sum total, just like when we had net force, the net work equals the change, that's delta, of kinetic energy. And hopefully you remember what delta means, right? Final minus initial, the change. So we can say that the net work equals kinetic energy final minus kinetic energy initial. That is the net work, the change in kinetic energy. And then we can even expand this because we know the formula, the equation for kinetic energy. So we can say work equals, so kinetic energy initial, let's assume the mass is not changing. So 1/2 mass times velocity final squared minus 1/2 mass times velocity initial squared. Guys, if it helps you personally to do F for final, I for initial, you can do that. It changes nothing. I just use this notation because that is the notation which it's in your formula chart. So I want to keep consistency with that, okay? Make sure you get this one down. Okay, so let's do an example to further illustrate what is work in terms of energy transfer. It says, a student uses a rope to pull on a 90-kilogram initially at rest block, which is on a cart of negligible mass. After some time, the block reaches a speed of 8 meters per second due to the work done by the student. Make energy pie charts for this situation when everything is part of the system. Okay, so again, I'm going to highlight things that I believe to be important. 90-kilogram block, which is initially at rest. And then negligible mass, so that means just the mass that we're going to consider is the 90 kilogram. So we do not include the cart. After some time, right, so at rest and then after some time, we're going to reach a speed of 8 meters per second due to the work done. That's very important. And make energy pie charts. So I'm going to, let's start with the schema. I'm going to do it on this side. So in this case, I'm going to simplify my system as much as I can. Of course, I'm going to have the block, right? Well, let's start with the student, right? The student is the one doing the work, literally. Just like you guys, and you guys do all the work sometimes. Student, and then there you go. And then, of course, we have the block, right? Because that's the work is being done onto the block. There you go. Now, some of you might say, and we have the earth as part of the system. Now, let me show you what is not necessary. So let's say we have a green student, right? So again, you're about to be delighted with my drawings. So we have the student pulling. Oh, it looks like he's squatting, right? So let's do the foot like that. So it kind of looks like. And then the student's happy because, oh, you can't even see it. Student is happy because it's the subject of a physics example. And there's the rope, right? Wait, the rope has to go through the hands. There's the rope, and then it's a red box or red block. Red box, like before Netflix, that's how you would rent movies. Maybe you can still see them at, I think, Walmart or Walgreens. So there you go. And this is 90 kilograms. And then some wheels. And then we have motion to the right. That's the direction of motion, right? And let's assume the angle is 0, just for the sake of this example, right? Meaning we're maximizing the work. So if you think about it, the Earth would be a factor for gravity, right? It would contribute gravity, or force of gravity by means of weight. But if you think about it, if you do the, let's just blow. Oh, I thought I was going to do the double arrow. You have the weight of the block, and you have the normal force by means of the wheels pushing against the force of gravity, against the weight, and the net force on the y-axis is 0. Well, not the net force, right? But the summation of forces along the y-axis is 0 because it's not moving up or down. It's the same case for the student, right? If you take the center of mass to be here, you have the weight of the student, and then you have the normal force by means of by virtue of them standing on the ground. So you don't have to include the earth. So there you go. Our system is simple. Again, try to keep it simple. There's the interaction, right? And then we're going to close the system. Or we're going to add a boundary. There you go. There's a boundary. Perfect. Now let's add the pie charts real quick. I don't want to I want to make this that long. So here's one. And there you go, at different times. Now I'm going to add the legend. I'm not going to do the little squares. I'm just going to use the highlighters to not make this so long. Okay, that's kinetic. Let's do potential and internal. There you go. So this is kinetic energy, energy of motion, potential energy, gravitational, and internal energy to account for the internal energy of the student, friction. In this case, we don't have any friction, right, for thermal energy, because we're assuming the wheels allow for no friction, even though there's friction. Again, we're simplifying this example because it's an introduction. So let's say the first, or time 0, is when the block is at rest. And then the second time, I'm going to say when the speed reached 3 meters per second, and then the last one is when the speed of the system was at 8 meters per second. So if the cart is initially at rest, then I know it's all internal energy because of the student, right? Let's assume the student ate some breakfast, right? No, Monster is not breakfast, guys. Don't do that. And then, so that's it, right? At rest, the motion for the block, student's about to pull, they have energy. Now, 90 kilograms is about 200 pounds, roughly. So, of course, after when the speed is 3 meters per second, then we have some kinetic energy, right? We're moving. And it is very plausible, I am almost certain that the student is getting tired even just a little. So we're going to do, let's say, this portion for kinetic energy, and the rest is internal energy, right? Even though the student is a little bit tired, then we have internal energy by means of the body temperature, right? So maybe they're breaking a sweat. So that's why then we keep energy conservation, right? Because we know the energy is just being transferred elsewhere by means of dissipation. And then when the student reaches 8 meters per second, then now we have more kinetic energy because we have a higher speed. And internal energy is here, but again, this is transferred because the student is getting tired, but we justify dissipation of energy by many things. Okay, so there you go. That's it, right? Energy pie charts. Now, that's because everything was part of the system, right? Oh, that was bad. Everything was part of the system. Let's just highlight, right? Just stick with highlighters. What if the student is the only part of the system? Well, I'm going to copy this, right, for the sake of time. There you go. Now, if the student is the only part of the system, then I don't need the block. That's it. And I close the boundary. There you go. Boundary closed. Okay. If the student is the only part of the system, then I need to change my pie charts because the student starts at rest, internal energy, right? Now the student is moving at 3 meters per second. However, now I cannot justify body temperature or sound energy or anything, and the student is just getting tired. So then I need to make my pie chart a little bit smaller because the student is using his energy to pull, right, to pull on the, or to move the block, right? And I think I'm going to get rid of the, oh no, not that. Oh, come on. Well, leave this one like that. Man, I can't do it. That's fine. And then notice how the internal energy is a little bit less. The pie chart's getting smaller. And then, let me use the small eraser because this is bothering me. So okay, no, that was not a good idea. That's fine. And then after, when their student reaches 8 meters per second, of course, they're using a lot more energy, right? Oops. Oh, that's fine. Well, I needed to make it even smaller. They're using a lot more energy. So they're going to be tired, right? We think they're going to be tired. Let me try to get rid of the color. Oh, man. There you go. I did it. Yay. So now we have an even smaller pie chart. And then at this moment, I'm pretty sure you're thinking, wait. Oh, I could have just, oh my God. Anyhow, you're saying, well, wait a minute. Doesn't this go against the law of conservation of energy? Isn't energy conserved, meaning it cannot be created nor destroyed, only transformed? Well, it is a matter of fact that the student's getting tired, right? So he's using his energy. So how can we justify the fact that the student is doesn't have the energy with which they started, right? That's why we have work, and we can justify or show that by means of an arrow. What this arrow means is there's work being done outside the system boundary because the boundary is just the student. So when the student is doing work outside the system, meaning outside the system is the block. So there's a transfer of energy from the student to the block, which is if the boundary has only the student, then the work done by the student goes outside the system boundary, which would be the block. And then over here, on this one, it's even more, right? That means energy being transferred or work done. That's what the arrow is, or energy transfer. There you go. Now let's assume after some time, and this is just to illustrate the point, the problem. He did it for like 5 miles, right? That's a lot to pull 200 pounds. And the student just passed out. So then there's no, let's assume there's no energy whatsoever. I know that can happen, but just all his internal energy, the energy from his breakfast, was completely gone when we can use a point. If you remember from geometry, a point has no shape, no size, no length, no width. So it's just a point. And we illustrate the fact that all the energy was transferred. I need to use blue to keep consistency. All of his energy was transferred out by means of work. And that's the very last, right? When the student's unconscious, no energy, it all went away. There you go. This is what you're going to do for your assignment. I am not going to do this one, at least for this video, how much work was done by the student, because of time. I don't want this to be that long. So I'm going to skip this one, and let's do the extension question. It says, unfortunately, all 4 wheels of the cart got stuck and caused friction between the floor and each individual wheel. Would friction be doing positive or negative work? Work can be positive or negative. The hint is friction with or against the motion? Now, if the student was pulling to the right, then friction would have a direction to the left, right? That would be the direction of friction. It's always against the motion. So in this case, friction is doing negative work. The reason why friction is doing negative work is the direction of the force of friction is against the direction of the force applied by the student. Don't forget that as per the equation, the first one we had, work equals force times distance times the cosine of theta, so direction matters. And then we can say negative work as friction is against motion. Think about what is the natural motion of the system, and then see if there are forces acting with or against it. If you have forces acting with the motion, it's positive work, and you have forces acting against motion, it's negative work. So for this example, let's say then friction was doing negative work, and then a friend of the student saw the student is struggling, right? Because they're not pulling, they're dragging the 200-pound block, or 90 kilogram. It's about 200 pounds roughly. So then the friend was helped or decided to help the student push. That other student, the friend, would be doing positive work because they would be pulling both to the right, and friction still doing work, negative work, because it would be to the left. I think that's enough. That's good for your assignment. Again, is related to these two. Don't forget that you can have work done, or you can have transfer of energy outside the system boundary or going into the system boundary. If the block was the subject, right, the only part of the system, then it would start with no energy because the block cannot do anything on its own because this is a thing. And then it would have an arrow going in because it's getting an energy transfer, right? So work is being done onto the block, so the arrow would be flipped, right? That is it. Be nice to the sub. Bye.